Today we're going to cover atrioventricular heart blocks. A heart block is a complete or a delayed conduction through the AV junction. That would be the AV node or the His bundle. What it does is it blocks the normal cardiac cycle. There are 4 different types of AV blocks that we're going to discuss today. We're going to discuss the first degree AV heart block. We're going to discuss a second degree AV heart block, type 1, and also the type 2, and the third degree AV heart blocks. The first thing I want to talk about are the area of the block in the AV node. Any sinus brady could be considered a supranodal block. So it's considered supranodal. If it's supranodal, that means that it is above the AV node. A first degree heart block is also considered supranodal, which means it occurs above the AV node. A second degree type 1 is considered a nodal block, which means that the block is occurring in the AV node. A second degree type 2 and a third degree are considered infranodal. An infranodal block occurs, I'm going to put below the AV node, but it's not really below, it's past the AV node, down in the His bundle or the bundle branches or something along those lines. The next thing I want to discuss is the severity of the blocks. Generally speaking, the higher the number, the more severe the block. So if you want to look at the first degree heart block over here, first degree heart blocks, they're not a true block. It's just a delay in the conduction system. People can live normal, healthy lifestyles with just a first degree heart block without any severe compromising of their cardiac output or perfusion status. When we talk about a second degree block, though, there's the type 1 and the type 2. If you were to have a second degree heart block, you would prefer to have the type 1 compared to the type 2 because type 2s can progress very quickly into a third degree or a complete heart block. Having a type 2 or a type 1 second degree heart block is still not a good thing because now you're kind of in the middle of the road when it comes to the severity of the blocks. The last block that you really don't want to have at all is considered a third degree, also called a complete heart block. That basically means that the atria and the ventricles are not communicating to each other at all and they both are beating at their own intrinsic rate. Let's start off with the first degree heart block. In a first degree heart block, just remember that it is not a true block, and so it's kind of a misnomer. We call it a first degree heart block, but realistically it's just a delay in the conduction system because for every P wave there is a QRS and a T wave. It's just a very long PR interval, but you still have a 1-to-1 P to QRS ratio. The prolongation of the PR interval means that the PR interval is going to be greater than 0.20 second. There's no clinical significance or very little clinical significance when it comes to first degree heart blocks. They are usually abbreviated first degree AVHB or just first degree HB. Sometimes people just put with a first degree, and that's fine too. Where the delay occurs is, if you look up here, this is a normal PR interval. We'll say this is a normal PR interval. Each color, as you can see, corresponds to a particular area of the conduction system all the way down to the ventricles. In a normal cardiac depolarization with a normal PR interval, you have your SA nodal depolarization that occurs right here, as you can see. The signal itself travels very quickly down to the AV node. Now the AV node holds the signal for this amount of time right here. This allows for this red bump right here, which as we see as a P wave, that is your atrial contraction or depolarization. Then it lets go, the signal right here hits that trigger zone. If you remember the trigger zone at the distal part of the AV node, it hits that trigger zone and then very quickly travels through the His bundle, the bundle branches, and the Purkinje network to allow for ventricular depolarization. And there's, of course, your Q wave, and that is traveling up there toward your R wave of the QRS complex. In a first-degree heart block, the problem is the AV node holds the signal for much longer than it's supposed to. So right here we have our SA nodal depolarization. Right here we have our atrial depolarization and hopefully atrial contraction. And this part right here, this whole thing right here is the time that it took for the AV node to hold the signal. As you can see, compare that right there to that right there, much, much longer. But if you look at the purple part here, which is the His bundle, then the bundle branch, then the Purkinje depolarization, all of this is the same time as all of this up here. The problem is the AV node holds that signal much longer, creating the first-degree heart block and the prolongation of the PR interval. Here are the characteristics of the first-degree heart block. You have a rate which is normally slow or normal. You're not usually going to have a sinus tachycardia with a first-degree heart block. That's a little bit more rare. It should be regular. The P waves are all present. For every P wave, there is one QRS wave. The PR interval is longer than 0.20 second. That's the problem, and that's the only problem. QRS width is normal or wide. The book where I got these pictures discusses the different types of variations of PR intervals. Some of these make sense, and I'm sure that every one of these is possible, but let's look at them. This one here, they'll say that the PR interval is 0.24 second. Since it's greater than 0.20, then technically, yes, it is considered a first-degree heart block. In this one here, the PR interval is 0.32, still considered a first-degree heart block because this P wave causes this QRS wave right here, QRS complex. Down here, the PR interval is getting wider and wider. This is a 0.41 second, and according to the book, this right here is still considered a sinus rhythm with a first-degree heart block. I don't know if over half a second is possible for a P wave to be held that long in the AV node to cause a QRS complex. According to the book, it's possible. Let's interpret some rhythms here. The atrial rate. We can still get an atrial and ventricular rate. Here's your P wave way out here. So we're going to get an atrial rate. 1, 2, 3, 4, 5, 6. We'll say 70. You have a ventricular rate that should be the exact same. 1, 2, 3, 4, 5, 6. It got cut off over here, but if your atrial rate is 70, your ventricular rate should also be 70 beats per minute. Regularity. I don't have calipers and I can't use this on here, so I'm going to go ahead and say just by eyeballing it, it looks regular. P waves are present and they are married, which means even though this P wave is way out here, it still causes this QRS complex. The PR interval, they were nice enough to calculate the PR interval for us, but if we wanted to do it ourselves, we could say there's 5 boxes, 6, 7 boxes. I probably would have put this at 0.28 second. They put it here at 0.31, but anyway. QRS complexes, it looks like they're nice and narrow, so I'm going to say 0.08 second. What's the problem? The PR interval is too wide. The rates are fine. It's regular. The P waves are present and married. The QRS is nice and narrow. The problem is the PR interval is too wide. So this is going to be a sinus rhythm with a first-degree heart block. I will tell you now there are a lot of issues with identifying these rhythms, these heart block rhythms. If you only put first-degree heart block as your interpretation, you will get it wrong. This is not the rhythm. This is the anomaly. This is the problem with the rhythm. You have to put the underlying rhythm first. In this case, the underlying rhythm is a sinus rhythm. The problem is that it has a first-degree heart block. First-degree heart block is not the rhythm. In this one here, you see these P waves. These are the P waves right here. You can see they're notched. This is pretty neat. I'd definitely do a 12 lead on this one. That's probably an atrial issue. So let's count the atrial rate. 1, 2, 3, 4, 5, 6, 7, 8. So we'll say the atrial rate is 80 beats per minute. The ventricular rate, 1, 2, 3, 4, 5, 6, 7, 8, is also 80 beats a minute. Regularity, it's just by eyeballing it, it looks regular. P waves are present and they are married to the QRSs. The PR interval, they were nice enough to calculate it here at 0.36, but let's see if we can do it also. We'll start right here on this line right here. So there's 5 little boxes, 6, 7, 8 little boxes, which gives me a 0.32 second, not 0.38, but either way, or 0.36, either way it's going to be wide. The QRS complex, it looks pretty narrow, so if we start here, it looks like 2 little boxes, 0.08 second. The interpretation, the only problem is at PR interval, first we have to put the underlying rhythm, which is a sinus rhythm, and now we put the problem, first degree heart block. Starting off by counting the atrial rate. This right here is a P wave. It's kind of tough to tell, but if you look at the PR interval here and look at the PR interval here, that looks like they just barely caught that P wave. 1, 2, 3, 4, 5, 6, 7, 8. So we'll say the atrial rate is 80 beats per minute. The ventricular rate, 1, 2, 3, 4, 5, 6, 7, is also going to be 80 beats a minute. Regularity, it looks regular. P waves are present and they are married. PR interval, this here tells us that the PR interval is 0.32 second, but let's do our own math and see if we can figure it out. Here's one that stops right here on this line, so there's 5, 6, 7.5 maybe, which would give me a 0.30, but 0.32, we're close. QRS complexes, now they look wide. Let's start right here since it starts on this bold line right here. 1, 2, 3. So it looks like to be about 3.5. So that would be a 0.14. So the QRSs are wide. Definitely want to do a 12 lead on this guy. Interpretation, there's a couple problems. First of all, it's the QRS is wide, but I'm more worried about this PR interval being wide here. So we have a sinus rhythm with a first degree heart block. This one might be a little bit tougher to tell. What they're doing here on this book arrows, they are pointing, this is the T wave, that is not a P wave. This right here is supposed to be the P wave. So let's go ahead and count the P waves. 1, 2, 3, 4, 5, 6, 7, 8. It says 9 over here, but we'll go ahead and count the QRSs too. 1, 2, 3, 4, 5, 6, 7, 8. It says 80. I'll bet that if you don't use the 6-second method, but if you use the countdown or the 300 or the 1500 method to calculate the atrial and ventricular rates, they'll come out the exact same, even though there's a discrepancy up here. Regularity, it looks regular. P waves, they are present and they are married. PR interval, they gave us the PR interval here, but let's do our own math to see if we can find a QRS that begins on a bold line. Doesn't look like there is one, so we'll just have to wing it. We have 5 boxes here, plus 1 right there, plus 1 right here, so that's 7 boxes, so we also have 0.28 second. The QRS complex does look wide, so let's start right here. There's 1 little box here, 2, 3, 4. So is that right? 4? 1, 2, 3. So it's actually 3. 0.12 second. Interpretation, the PR interval is wide, so we're going to say it's a sinus rhythm because our heart rate is 90 with a first degree heart block. This one looks a little bit slower, so let's go ahead and count the P waves. This is a little tough because here's that P wave right there. Look how drawn out that P wave is right there. You'd also want to do an EKG on this person because that P wave does not have the proper morphology. So let's count our P waves. 1, 2, 3, 4, 5. So we have an atrial rate of 50 beats per minute. Ventricular rate, 1, 2, 3, 4, 5. It's easy when there's not a lot of ventricles or QRSs on there. Regularity looks regular. P waves, they're flattened out, but they are present and they are married to the QRSs. The PR interval, they calculated at 0.25. I'm not going to be able to get 0.25, so I'm going to do my own calculations here. So let's start right here. The P wave kind of begins on this bold line right here, so we know that's 5, 6, 7. So I'm going to say that the PR interval is actually 0.28 second. QRS complexes do look narrow, 1, 2 little boxes, so 0.08 second. The problems that we have, the rate is less than 60 and the PR interval is greater than 0.20 seconds, so we're going to say this is a sinus bradycardia. Always put your underlying rhythm first with a first degree heart block. All right, let's move on to the second degrees. First, we're going to discuss the second degree heart block type 1. Second degree heart block type 1 is also commonly referred to as Wenckebach because this was the guy that kind of discovered the whole second degree type 1 heart blocks. The intermittent conduction through the AV node is the problem. It's an intermittent conduction which results in a resetting of the AV node itself, and I'll discuss what that means in a minute. What is specific about a Wenckebach is that the PR interval increases. It doesn't stay the same like it does in the previous rhythms that we've discussed. The PR interval will widen as you get closer to completely dropping a QRS complex, which means you end up with an extra P wave. The AV node will then rest, and then the next PR interval will start over again, and you'll repeat this process. The concern we have about this is that if we're dropping QRS complexes, we can have a decrease in cardiac output. So let's talk about how a Wenckebach occurs and how the prolongation of the how the prolongation of the PR interval occurs. We have 3 impulses that are going to head down to your AV node right here. So here's impulse A, impulse B, and impulse C. Impulse A hits the AV node, and it rifles through the AV node. It's delayed, but then it rifles through the AV node like it's supposed to, giving you a normal PR interval. Unfortunately, as this impulse travels through the AV node, it depolarizes the AV node. Now, if you remember the all or none principle of cellular depolarization, if a cell reaches threshold, I'm going to do this little picture again here, best I can. If a cell reaches threshold, it will depolarize every single time. The problem is not all cells have the same threshold. So cells that depolarize first will repolarize first. Cells that depolarize last will repolarize last. What that does is when this impulse heads through that AV node, as repolarization occurs, it leaves this checkerboard of repolarized and depolarized cells because they're not all going to repolarize at the same time. As impulse B reaches the AV node, because not all the cells have repolarized yet because of some kind of issue with the AV node, the signal is slowed down even more. What that does is it causes a prolongation of that PR interval. As you can see, when impulse A went through, it was fine. Impulse B took a little bit longer. As impulse B goes through the AV node, it redepolarizes more cells that are trying to repolarize. When impulse C gets there, there are so many cells that have not repolarized that the impulse cannot make it to that star right there, which is the trigger zone. The trigger zone is where the impulse speeds up again and gets into the His bundle. In this case, because the signal never made it to this trigger zone right here, you're going to have a P wave without a QRS complex, and then you're going to start all over again with the first impulse that will give you a normal PR interval with a QRS complex. The pattern that you will see here in an example like this is that you're going to have this normal PR interval. This PR interval right here is normal, 0.16 second. Then this PR interval will be prolonged when the next impulse hits. Then this PR interval will be prolonged even more. And then what will happen is you'll have a P wave and no QRS complex. What's interesting about this is that this is your P to P interval. Your P to P interval is going to march out every single time. The reason for that is because the SA node is still sending out the signal like it's supposed to. The problem is at the AV node, and it is not letting the signal through at the same rate. So your QRSs are going to be irregular. Your P to P interval, though, is going to be normal. In the characteristics of a type 1, I'm talking about a type 1 up here, the rate is usually slow or normal. It's usually not a sinus tachycardia, but it can happen. When we talk about irregularity, it's the R to R interval, which is irregular. The P to P interval is perfect. The R to R, though, is going to be irregular. P waves are going to be present, but they're not going to be all married. Some of the P waves are not going to be causing QRS complexes. So the P to QRS ratio is going to be however many P waves you have, you're going to have the same number of QRSs minus 1. So if you have 2 P waves, you'll only have 1 QRS. If you have 3 P waves, you'll only have 2 QRSs, and so forth and so on. Your PR interval will be widening. This is not how I want you to document this. I don't want you to put widening because I want you to practice measuring all of the PR intervals. Your QRS width could be normal or wide depending on any kind of QRS problems. The atrial rate in this case, let's look at the atrial rate by using the 6-second method. 1, 2, 3, 4, 5, 6, 7. So we'll say that the atrial rate is 70 beats per minute. What's interesting about this is that if you were to take your calipers and march out these P waves, they would march out perfectly. Ventricular rate, it looks to be about 50. The regularity is going to be irregular. If we had a longer strip, you would probably see a pattern. As you see here, you see 2 beats and a pause, 2 beats and a pause. If we had a longer strip with 2 beats and another pause, you could call this regularly irregular. P waves are present and married except at the block. If you just put present and married, you will lose points because they're not all present and married. The PR interval is going to be kind of a pain here. So we look over here, and this PR interval looks to be about, let me see, 1, 2, 3, 4, 5. So it's 0.20. This one here is, that looks like 3. That's 7. So it looks to be 0.20 to 0.28 seconds widening. And then it drops. The QRS complexes all look pretty good, so I'd say they're about 0.10 second. The problem here is that our PR interval is widening, so that would be, always document your underlying rhythm first. Sinus rhythm with second degree heart block type 1. In this one here, this is kind of helping out a little bit because this is a very complicated rhythm strip to look at here. So fortunately they were nice enough to put the blue dots down here which resemble the P waves. This arrow is pointing at a possible P wave buried in this T wave right here. So let's pretend, just for this sake, is that there is a P wave buried in there. Let's count the atrial rate. 1, 2, 3, 4, 5, 6, 7. Ventricular rate looks to be about 60. Regularity is going to be irregular. P waves are present and they are married except at the block. PR intervals. They were nice enough here to do the math for us, and for time's sake, I'm going to go ahead and just use their numbers here. Here they say it's greater than 0.46 seconds, but I would actually like to do the math to figure out exactly what is the PR interval. If that is a P wave that is buried in there, that would be your dropped beat. So you'd have 4 P waves and 3 QRSs. The PR interval, we're going to say it's 0.26, 0.46, and then 0. Whatever this is here. So that's 5, 6, 7, 8, 9, 10, 11, 12, which would give me a 0.48 second, and they are all widening. The QRSs look a little bit wide, so they look to be about a 0.12 seconds. Problem is the PR interval is widening, so we have an underlying rhythm of a sinus rhythm with second degree heart block type 1. Last one. This one here, these bumps right here, those are the P waves. Those look really weird. Hopefully, since this is lead 2, you'd be doing a 12 lead on this guy. Atrial rate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Wow, 13. So our atrial rate is 130 beats per minute. What's our ventricular rate? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 90. That seems like a big discrepancy there. We might have to do the math to figure out what it is. So the regularity is going to be irregular. Because you have groupings of 3 right here, you can say that it's regularly irregular if you wanted to. P waves, they are present and they are married, except at the blocks. The PR interval, well, let's start with this PR interval right here. So we start, that's a kind of a tough one. Let's start with this one. There's 1, 2, 3, 4, 5. So it's 0.20. And then this one here looks to be about 5, 6, 7. 0.28. Supposed to be commas right there. The last one is 5, 6, 7, 8. 0.32 seconds, and they are all widening. QRS complexes look to be about 1, 2, so 0.08 second. Interpretation would be a sinus tach, because you have 130 heart rate here, with second degree heart block type 1. Let's talk about a second-degree heart block type 2. The difference between a second-degree heart block type 1 and a second-degree type 2 is that in a type 2, the PR intervals do not extend. The PR intervals are constant, but you are still dropping beats somewhere. So they're less common than type 1. They're more serious and could eventually progress into a complete heart block, which we also know as a third-degree heart block. It's an intermittent block of the AV junction, kind of like what a type 1 is, but in this case, the problem is the PR interval doesn't change. They most commonly occur in the bundle branches past the AV node. That's why a second-degree type 2 is called an infranodal block. For example, you have a PR interval here, and let's just pretend that this is a normal PR interval of 0.16 second. These are all going to be consistent. All of your PR intervals are going to be consistent. This will be a 0.16 second. This will be a 0.16 second. All of these PR intervals are going to be constant, but you will have a dropped P wave, or I'm sorry, you will have a dropped QRS with this P wave. In this picture, it shows a grouping of 2 and then a drop, 2 and then a drop. That's just the picture. This doesn't always happen. You could have 1 QRS and then 1 dropped. You could have 3 QRSs and then 2 dropped. The pattern is so random that you might not have something as simple as this. Looking at the characteristics, usually the rate is normal to slow. It doesn't always go faster, but it can, as you can see in one of the other ones. It could be irregular, and like I said, this is the R to R interval, which could be irregular. P waves will be present, but they won't be married. They won't be married at the blocks. P to QRS ratio, there is no pattern. If you remember, the type 1 was a number to a number minus 1. Minus 1. In this one, it's not like that at all. It could be a variable. There's no pattern. So the PR interval could be normal or it could be wide. The QRS could be normal or wide as well. Let's interpret some rhythms. As you can see here, the blue dots are pointing out all of the P waves. And if you look at all the PR intervals here, the book was nice enough to march these out for us. They are all consistent. They don't get wider like they do in the type 1. So let's calculate our atrial rate. 1, 2, 3, 4, 5, 6, 7, 8, and we'll say 8-ish. Ventricular rate, 1, 2, 3, 4, 5, 6, 7. Regularity, if you look at all of your R to R intervals, it is irregular. P waves are present and married, except at the block. The PR interval is pretty wide here, so let's calculate it just for fun. There's 5 boxes. There's 6, 7, 8. So we'll say it's 8 boxes, so that's a 0.32 second. QRSs, they look good. They look narrow, they steep angles, sharp points, all that stuff. So we're going to say that it is a 0.08 second. Notice that you have a really wide PR interval here. The problem we run into is, how do you document this? Start off with the underlying rhythm. It's a sinus rhythm. Okay. Then we have another problem. We have a second degree heart block type 2, and you can go a couple different ways with this. We still have to document this prolonged PR interval. You could say it's a sinus rhythm with a second degree heart block type 2 with prolonged PR interval, or you could say with a first degree heart block. Some people get weird when you say sinus rhythm with a second degree and a first degree, because they think, oh, well, you have to pick one. Technically, both problems are going on here. Either one of those would be correct. Second degree heart block type 2 with a first degree, or second degree heart block type 2 with a prolonged PR interval. On this rhythm here, we have an atrial rate of 1, 2, 3, 4, 5, 6, 7, 8. Ventricular rate, 1, 2, 3, 4, 5, 6. Regularity, this is fun because now this has 2 beats, a space, 2 beats, a space, 2 beats, so we could call this regularly irregular. P waves, they are present and they are married, except at the blocks. PR interval is going to be consistent except where the block is. So let's look right here. We have 1 box, 2, 3, so it's about a 0.12 second are all the PR intervals. QRSs, they're wide. See that extra notch in there? That's actually making it wide, so it starts here. 1, 2, 3. So we're going to say the QRS is 0.12 second. The underlying rhythm is going to be a sinus rhythm with second degree heart block type 2. Last one, atrial rate, 1, 2, 3, 4, 5, 6, 7, looks to be about 8. Ventricular rate, 1, 2, 3, 4, 5 and a half, so we'll say 55. for fun. Regularity is going to be irregular. P waves, they are present and married, except at the blocks. The PR interval is going to be consistent, but it is going to be very wide. So let's look at this one here. That's 3 boxes, 4, 5, 6. Let me see here. 3, 4, 5, 6. Yep. So it will be a 0.24 second. QRS complexes look a little wide. So there's 2, there's 3. So the QRS complex is 0.12 second. The interpretation, underlying rhythm is going to be a sinus rhythm with second degree heart block type 2. Now let's discuss a third degree heart block. This is the most dangerous heart block out there. It is a true heart block. In a third degree heart block, this is a true complete heart block where the atria and the ventricles are beating independently and there is no communication between them. This atrioventricular septum right here, for whatever reason, has completely blocked all communication from the atria and the ventricles. This will result in 2 separate rhythms. You have your sinus rhythm, which is just a bunch of P waves, but then you have your ventricular escape rhythm down here, which is just a bunch of QRSs. There is no communication between the two. How this develops on the monitor, as you can see here, this is what we would see on the monitor, is what this black rhythm is down here. So we have a supraventricular rhythm, which is nothing but P waves. We have a ventricular rhythm, which is nothing but QRS complexes. And then what we see are a bunch of P waves and QRSs that have no correlation to each other at all. When it comes to the characteristics, the atrial rate is normal. It could be running at 70 beats a minute. The ventricular rate for itself could also be normal. You could have a ventricular rate of 60 or 50. So they're both normal within themselves, but they are not communicating. Regularity for the P to P and the R to R intervals will be regular. They just won't be marching out. P waves are present, but they will not be married. Not even a little bit. If it looks like they are, then it's just a coincidence. The P to QRS ratio does not exist. PR interval, there isn't one. If the P wave does not cause the QRS complex, then you cannot have a PR interval. The QRS width, it could be normal or it could be wide. If the ectopic focus that is causing the ventricular rhythm is higher up in the bundle branches, you might have a more narrow QRS complex. But normally, third degree heart blocks, the QRS will be wide. In a third degree heart block right here, we have our atrial rate. They've been nice enough to show us where the atria are depolarizing based on these little blue dots here. So let's count these. 1, 2, 3, 4, 5, 6, 7. So we'll say the atrial rate is 70 beats per minute. The ventricular rate, 1, 2, 3, 4. So we'll say the ventricular rate is 40 beats per minute. What I'm looking at here at the ventricles is this right here is the QRS. That right there is the ending of the T wave. So that is an extremely prolonged PR interval, which is what we discuss later in 12 lead. What I see over here, though, is there's a P wave that's occurring right there in that ST segment. That's kind of interesting. So let's look at our regularity. If I had calipers, I would bet that the R to R intervals are regular. P waves, they are present. Not married or not associated. The PR interval, none. If the P waves are not married or not associated, you cannot have a PR interval. If you measure PR intervals on my homework, I will mark them wrong because the P wave does not cause the QRS. The QRS complexes are a little wide. They look to be about 0.12 second. This is one of the weird rhythms where you do not have to put down an underlying rhythm. If you say sinus rhythm with third degree heart block, you will not be wrong. If you only put third degree heart block, this will also be accepted. If you say third degree heart block, people automatically know what you're talking about. If you want to be 100% accurate, technically it is a sinus rhythm with a third degree heart block. The atrial rate here has been counted for us by the blue dots from the book, so we're going to go ahead and call that 60 beats per minute. The ventricular rate is 40 beats per minute. I'm just using the 6-second method here. Regularity is going to be regular. P waves are going to be present, not married. The PR interval is going to be none. QRS complexes are looking really good, actually. They're looking nice and narrow, so the ectopic focus to depolarize the ventricle must be higher up in the bundle branches in that area, or even closer to the His bundle. So I'm going to say 0.08 second for the QRS complex, and once again, you can either put sinus rhythm with third degree heart block, or you can just put a third degree heart block. Here, the book was nice enough to show us all of these atrial rates down here, or atrial depolarizations down here. There's 8 of them, so 80 beats per minute. Ventricular rate is about 40 beats per minute. Regularity is going to be regular. P waves, present, not married. PR intervals are going to be none. QRS complex, these puppies are really wide. What the arrow here is showing is that that extra little bump right there is not part of the QRS complex. So you don't want to take that into consideration when measuring your QRS complex. Same thing right here. So let's start right here with this one. There's 1, 2, looks like 3, 0.12 second. And our interpretation would be third degree heart block. Another one here, we have our atrial rate, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'll say the atrial rate is 90 beats per minute. The ventricular rate, 1, 2, 3, 4, that's a huge discrepancy between those numbers, 90 and 40. What they were doing here is they're showing us where we can find these P waves. There's a P wave buried in this T wave right here. The arrow is pointing to where it is, but if you look at this T wave and you look at this T wave, they look different. So that tells me that there's an extra depolarization going on here. And I would say the same thing right here. There's an extra depolarization going on in that T wave because that T wave and the one back here are completely different. So I would be able to march out if these are the normal P to P interval. If I use my calipers, it would fall right here. Then if it would fall right here, and then, oh, look at that, there's one right there, and then we move over, and there'd be one there, there, and there'd be one buried in that T wave. Regularity is going to be regular. P waves are present, not married. The PR interval is going to be none. QRS complex, I can't use this right here because this one actually has a P wave buried in it. Let's use this one right here. So I have a 1, 2, 3, 4. So the QRS in this case is going to be 0.16 second. Interpretation, third degree heart block. I'm going to do one more rhythm here, and I really like this last rhythm because it's definitely a brain teaser, so we're going to walk our way through it. For this rhythm here, you want to start off with the atrial rate, and this is really important to follow the step-by-step process when you do this. Ideally, what you want to do is you want to find your P to P interval and march backward in your P to P interval. When you just glance at this rhythm, the first thing you think is that it is a sinus rhythm that goes into ventricular standstill. And that's not what's happening here. If you were to look back at these P waves here, there's a P wave actually marched right there. There's a P wave right there. There's a P wave right there. So as you can see, there are P waves that are buried in those T waves. This changes your sinus rhythm into a ventricular standstill into a different rhythm. So let's go ahead and count our atrial rate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we'll say the atrial rate is 120 beats per minute. The ventricular rate, though, looks like it was about 60 before it went into ventricular standstill. So 300, 150, 175, 60. So it's about 60 beats per minute down to 0 beats per minute. Regularity, well, it was regular and then it went irregular. So I'm just going to call this irregular. P waves are present and married except at the blocks. This P wave does cause a QRS, and that P wave does cause that QRS. The PR interval initially looks to be, I would say, 0.20, maybe a little bit wider. I'd have to get some calipers to look. So it's 0.20 when it is present. QRS complex does look a little wide, though. So if we start here, there's 3-4 boxes, so we're going to say 0.16 second. So the underlying rhythm here is a sinus tachycardia based on the rate with a second-degree heart block type 2 into ventricular standstill. I hope you enjoyed this presentation of the AV heart blocks. It's definitely one of the shorter presentations. If you have any questions, please feel free to contact me. Thank you.